Good evening, everyone. Welcome to this first live session for NPTEL course Nanobiotechnology Enabled Point of Care Devices. The actual live interactive session could not be recorded due to some technical glitch. So, I'll be re recording it for the purpose of YouTube viewers. So, welcome to this session. This is the course code for this course is NOC 24 G23. This is the first live interactive session. The course instructor for this course is Professor Gorchan Datta, School of Medical Sciences and Technology, Indian Institute of Technology, Kharagpur. Today, myself, Amey Dukle, Prime Minister's Research Fellow, Department of Mechanical Engineering, IIT Tirupati. I'll be the mentor for this live interactive session. So we just before we begin, there's just a few important points. So this live and interactive sessions are just to boost your performance. These are not compulsory, but we highly encourage you because these will give you a perspective of what kind of questions will be asked in the exam and how what is expected from you. I request you to be respectful in the chat. Especially, I would say actually try to limit the use of chat. Try to unmute yourself and ask your question right away. And questions can be asked at the end of session. This can be regarding the first week assignment, first week lecture material, and even something if you want to know extra research papers or something for your research, you can also ask some questions on that basis. The video will be uploaded on YouTube. This is the link to the YouTube channel. So let's begin. So the plan of this session is to discuss practice assignment 0, then we discuss practice assignment 1, and then conduct a question answer session. So this is the course outline. So it is a 8-week course, and this is the first week. So in this week one, we continue introduction and basic concept of point of care diagnostic, analytical chemistry, and biological applications. With biological applications and their mechanistic studies in diagnostic, thermodynamic, chemical kinetics, and the rate constant. So let's begin. So, but before we begin, actually, I'll just give you an overview of what point of care testing is and why it is important. So, basically, point of care testing, as the word says, is the testing that is taken care at the point of care. Basically, in normal case, per se, a person A has fever. So, in that case, he will go to the doctor. The doctor in his as per the basic treatment protocol will look at the symptoms. So if the symptoms are very clear, he may go with the specific treatment protocol. But if the symptoms are not very clear or if they are developing, so the doctor will prescribe with paracetamol, which is the basic uh, treatment for any fever. But now what happens is if the person is having something else, so if he is having a malarial fever, so the difference is in the normal fever, the fever is because of a virus, whereas in malarial fever, malaria is a parasitic infection. It is not a viral infection. So the administration of paracetamol can in a way actually lead to elevation of some toxins inside the body, and which will increase the malarial load in the body. So it is so this makes the case for blood tests very essential. But again, in a country like India, the blood testing labs are not very widely available. So in metros they are widely available, but in the rural areas they are not widely available. And even where they are available, the lead time that it takes to from sample submission to the result coming is quite long. That also leads to people losing out on the critical time that is required for saving a patient. So in this case, the point of care testing comes into play. So point of care testing does the testing at that place, at that, and gives the result within minutes or within maximum in 15 to 20 minutes. So this saves a lot of time, and this also gives the important things, important information to the doctor, so that he can start the treatment as soon as possible. This and this will play a important role in saving the life. So you have to understand that this is a very important field, and especially in the country like India, it has great potential. So with this, let's begin. So with the week zero assignment. So okay. So so the question one is, reduced graphene oxide is 1D nanomaterial, 2D nanomaterial, 3D nanomaterial, or a quantum dot. So a nanomaterial is a material where the dimensions are between 1 to 100 nanometer. So in case of 0D nanomaterial, all the dimensions are within 1 to 100 nanometer. In 1D nanomaterial, only one dimension is more than 100 nanometer. In 2D nanomaterials, two dimensions are more than 100 nanometers. In 3D, likewise, all the dimensions are more than 100 nanometers. Quantum dots are basically nanoparticles or 0D nanomaterials. So, any guesses on this question? Okay, so the correct answer is 2D nanomaterials. Basically, reduced graphene oxide has X and Y axis are more than 100 nanometers, so it is a 2D nanomaterial. But the Z axis is less than 100 nanometer, so it is between 1 to 100 nanometers, so it is a 2D nanomaterial. So yeah, so coming to question two. For biosensing analysis, dash transducers are the most commonly used analytical techniques, often used when the research group. Options are voltammetric, conductive, potentiometric, volumetric. So basically, in voltammetric, so there are three main types of transducers. One is voltammetric, potentiometric, amperiometric. So amperiometric, as the name suggests, the voltage is constant, and the current is measured. In potentiometry, the current is constant and the voltage is measured. In voltammetric, basically the current is measured by varying the voltage. So you can have step, in step form the voltage might be increased, or in any other manner the voltage will be increased and the current will be measured. So basically now, from these three technologies, in like majority of the sensors are done. So amongst this, so with our answer is voltammetric is the most commonly used detection technique. This is because it has excellent sensitivity, and it has very large useful linear concentration range. So in terms of amperiometry and potentiometry, the range is quite low. In case of potentiometry, the sensitivity is also not quite good. In case of amperiometry, um, the range is quite limited. So voltammetry is the most commonly used technique. So let's go with the question third. In a three electrode system, the current flow is between the working electrode and the reference electrode and the counter electrode, working electrode and the counter electrode, both these both A and B. So basically, a normal electrochemical cell has only two electrodes, that is a cathode and the anode. But in case of electrochemical sensors, we have three electrodes. One is a reference electrode, working electrode, and a counter electrode. So here it's the setup. So in this you can see that we have three electrodes. So one is the reference electrode, working electrode, and counter electrode. Working electrode is where all the detection takes place. So due to the detection, there will be change in the current or the voltage occurring at that electrode. So that is why the what and what that is what is detected. So basically the current flow or the voltage between the working electrode and the current and the counter electrode is what is measured for the detection. So in this case, the answer is the current flow is happening from the working electrode to the counter electrode. So coming to the question four, to achieve ultra-sensitive detection, it is essential to choose a redox cycling system where all the site reactions should not be kinetically slow, tedious, propulsive, and inert. So basically, in a normal scenario, basically you'll have a substrate, you'll have a detection element, and the analyte. Analyte is what is being detected. So in that case, what will happen is the signal generated will be quite low. So that will be very difficult to detect in using our electrochemical sensor. So what we do is we increase the flow of electrons. To increase the flow of electrons, we do a secondary uh, a detection material with some gold nanoparticles or some labeling elements such as gold nanoparticles, and we do it such that with the secondary labeling, there will be some reactions, side reactions that will be there will be some reactions that will be triggered. uh, these reactions will increase the electron flow. But now, since it's a biological element, it will have more than the analyte as well. So if per se, if we are sensing something, sensing glucose from the blood, it is not just that the blood will have glucose. Blood will have the WBCs. Blood will have oxygen. Blood will have hemoglobin, etc., etc., etc. And these biological substances also react with the biorecognition elements that are quoted on this sensor. So these are called as these reaction between so other than glucose, the reaction between elements other than glucose with the biological recognition element are known as site reactions. So logically, what we would want is that the site reaction should be as low as possible so that the background noise or the wrong readings are as low as possible. So only we would always want that the sensor detects only what we want. So that is why the answer to this question is that the side reaction should not be propulsive. So they should be tedious or inert. So it will always be recommended that the side reactions are inert, but even if they are slow enough that our main reaction occurs and we have gotten the data, that's enough for us. So we are our main aim is that the side reaction should not be propulsive in nature. So coming to the question five, the most famous commercial home glucose sensor works on which principle? So electrophysiological principle, electrochemical principle, physiochemical principle, chemical principle. So the answer is electrochemical principle. So basically, what does is it has a platinum electrode that is coated with a semi-permeable membrane. Uh, that is coated with an enzymatic layer. So what happens is when the glucose sensor is dropped on the uh, glucose that goes through the capillary action. So when you actually prick it through capillary action, the blood sample travels up. So first it travels, first it meets the enzymatic element. So at the enzymatic element, the glucose is turns into gluconic acid. Glucose in presence of glucose oxidase, that is the enzyme that is present, turns into gluconic acid and also release H2O2. So the H2O2 passes through the semi-permeable membrane and reaches the platinum electrode where it is oxidized, and it releases and it reaches the platinum electrode, and there it uh, releases oxygen and electron. So it is reduced at that um, platinum electrode, and the electron which is released uh, is correspond the amount of electrons released correspond to the amount of glucose in the blood. So higher amount of glucose, higher amount of H2O2 will be produced and higher amount of electrons will be released. So this is how the mechanism is working. So it will have a and again it will have a three electrode setup: reference electrode, working electrode, and counter electrode. So the Answer to this question is electrochemical setup. So, which of the following techniques is used for cleaning so the coming to the next question, which of the following techniques is used for cleaning the transistors before manufacturing? So, the options are oxygen plasma cleaning, nitrogen plasma cleaning, argon plasma cleaning. So, it is not silver; it's argon plasma cleaning, and all of these. So, basically, what we have to do is basically when what happens is when the transducer surface is there, even if there are fingerprints or something like that, there is organic matter. So what happens is because of these organic matters, the surface becomes hydrophobic, so that it doesn't allow the materials we actually want to, or the biorecognition elements we actually want to coat, to not attach to the surface. So for that, it is very important that we clean the transducer such that we can get maximum addition of the biorecognition element to the surface. So in this, our first step will be cleaning with plasma. So the correct answer for this is we use all plasmas. We all the plasmas will work because every plasma will break the bonds between the organic substrate on the organic impurities which are already existing on the transducer, and this will allow for better addition of the materials which we want to actually coat on this. So it will basically plasma cleaning will increase the hydrophilicity, that is the ability to spread on this surface, and from that, because of the increased hydrophilicity, we'll be able to get more proper surface modifications on the transducer surface. So moving to the next question. So the cathodic part in the electrochemical cell and has oxidation reduction, pseudo oxidation, pseudo reduction. So basically, it's a very easy thing. It's a very confusing thing, but yet there is a easy way to remember it. So basically, you can just remember by the thing called care. So Ca is cathode and Re is reduction. So this is a trick where you will never go wrong when at this kind of questions. So basically, they are very simple questions, but there are many times people go wrong in this type of questions. So very important. In an electrochemical cell, there are two electrodes, cathode and anode. Uh, then the at anode there is oxidation happening, and at the cathode there is a reduction happening. So it is very important to remember it. Just I remember the word care, Ca, cathode reduction. So when you know the cathode is reduction, you can go for anode. You can easily know it as oxidation. So yeah, there is nothing called pseudo oxidation and pseudo reaction that in a typical electrochemical cell. In complex cells there might be something like that, but at least in the typical cells there is nothing called pseudo oxidation, pseudo reaction. Okay, so coming to the next question. Commercially available point of care pregnancy test kit is based on which of the following assays? Electrochemical impedance spectroscopy, lateral flow, surface plasmon resonance, optics. So basically, these are the detection techniques that are used for detecting the readings. So EIS is basically you put a specific electrical uh, profile, VI profile, and then you count the impedance. So that is EIS. Then there is lateral flow assay. Basically, they where as you say, as the you can hear, it is just the flow that is happening in on one substrate layer. So that is called as the lateral flow assay. Surface plasmon resonance is basically optical technology wherein you basically you put light, and then you measure the uh, output, the reflectance or the resonance that has been happening. So for this we use the labeling elements such as gold or other nanoparticles, and then we just measure the resonance that is happening. So If more detect analytes have been detected, there will be higher resonance. So using that, we can find out the readings. And optics are basically through visual, through the use of optical devices such as a camera phone or uh, a microscope. Basically with camera phone it is picking up very rapidly, but the problem is every camera phone has a different optical properties. So that is why it is not very easy to actually scale up for commercial applications. So that is one of the problems. But yeah, coming to our latter pregnancy test kit. So pregnancy test kit is just a plain paper based it is a device with nitrocellulose substrate. So that substrate is coated with the is where the sample is taken. It has a sample pad, then it has a conjugate pad, then it is a test zone, and then there is a control line. So basically, the sample is first labeled. Then, if it is positive, it will hit in the test zone. The SA will happen, and you will see a positive line in the test zone. If the if the it is negative, then uh, then the conjugation will happen in the control zone, and you will see the control line which will be glowing will start appearing in your test. So these type of tests are called as the lateral choices. Okay, so moving to the next question, which is the following is a biorecognition element, enzyme, antibodies, DNA, all of the above. So the answer is basically all of the above. So sensors are used from all these devices for all these biorecognition elements for making sensors. So basically, enzymatic sensor. One of the examples I can give you is the glucose sensor. So for antibodies, basically the example we just discussed before, which is the pregnancy test kit, and DNA-based sensors are also being widely used in terms of if you read the literature regarding COVID tests. So COVID test, yeah, so the COVID point of care testing kits. So for that, DNA-based devices, DNA-based and biorecognition elements are also being widely used. So yeah, coming to the next question, which of the following is not a biosensor? So we have the options as immunosensor, pregnancy test kit, glucometer, pulse oximeter. So glucometer, as I showed you, as we discussed before, glucometer has a biorecognition element of glucose oxidase. So basically, first let me tell you what is a biosensor. So biosensor is basically anything that uses a biorecognition element. So coming to the glucometer we have already discussed. It has glucose oxidase as the biorecognition element that makes it a biosensor. So pregnancy test kit, again we discussed it. It has antibodies which are again biological recognition elements. So it again is a biosensor. Immunosensor, basically it is used for disease detection. It is used for detecting what stage a particular disease is. So again, for that, again the antibody detection is what is the mechanism used. So again, it is a biosensor. But in terms of pulse oximeter, as you can see, there is the biorecognition. There is no biorecognition element. We have two LED lights and a detector photosensor. So in this case, there is no biorecognition element involved. So it is a not a biosensor. Again, the similar example is your heart blood pressure monitor. These devices are for biological application. They are measuring the biological parameters inside your body, but these are not biosensors per se. These are sensors for biological application, but these are not biosensors. So please keep that in mind. Keep understand the difference between a biosensor and a biological the sensor used for measuring biological parameters. So keep that in mind. So with this, we end the practice assignment 0. Let's go with practice assignment 1. So let's continue with the week 1 practice assignment. So let's start with the first question. So basically, the first question is nanoparticles are usually defined as particle of matter that is between radius 1 to 100 nanometer, 10 to 1000 angstrom, 5 to 500 angstroms, A and B both. So basically, this is a trick question. Basically, because just few minutes back, I have told a nanoparticle is a matter which has dimension between 1 to 100 nanometers. So everyone will be inclined towards selecting A as the answer. But again, you have to read the question very carefully. There is something called as radius. The question asks what is the radius of the nanoparticle. It is not asking for a time for the entire size of the nanoparticle. So basically, a nanoparticle size is obviously between 1 to 100 nanometers, but the radius is half the size, so it can be between 5 to 50 nanometers, and 1 angstrom is 0.1 nanometers. So again, that means 0.5 nanometers is 5 angstroms, and 50 nanometers is 500 angstroms. So that's the answer is option C, 5 to 500 angstroms. So I hope everyone is clear with this. This is something which tells you that you need to be very attentive when you are writing the exam. Don't just blindly look at the first few letters and just tick the options. Please read the question carefully till the end. This is how the exam will be. It will try to test not just your knowledge but also your patience and how you are writing, how you are attempting it. Please be careful with it. So coming to our next question, for Thal functionalization, which of the following catalysts can be used? So we have options CDC, 2MEA, NHS, EDC, NHS both. So basically, in most of the examples which have been listed in the course, or even if you find in any literature, EDC and NSS will be the most commonly used catalyst for biosensor related applications. But for thiol functionalization, 2MEA is used. So why is thiol functionalization done? So basically, to cause the attachment between the nanoparticles and the antibody, we need uh, some kind of attraction between the two. What we do is basically we functionalize the nanoparticle surface with amide groups so that there is a NH bonding between the particle and the antibodies, and then they'll be conjugated. So then they'll be attached together, and they can be used for labeling them. For that, we use thiol functionalization, and for thiol functionalization, 2MEA is the catalyst used. So question 3. Which potential is important to avoid contamination for metal salt in the electrodeposition application? Negative, positive, neutral, both A and B. So why is it done? So basically, what we do is we have a substrate. Uh, so the answer is negative potential. So actually, how it is done is we have a substrate. On the substrate, we put salts of gold. So HAuCl4. So for that, the oxidation number is +1 for hydrogen and -4 for chlorine. So the net oxidation number is -3. So the thing is, so it means that it needs 3 electrons, after which it will get reduced to gold. So in this, what we are doing is we are adding the electrons. So to add the electrons, we need negative potential. So that is why for electrodeposition applications we use negative potential. So going to the next question, which kind of electrodes are important for specific signal generation? So this is from the previous assignment. We spoke about fast propulsive TDS. So this is how these are the applications we are seeing. So basically, the in the first option, we have the labeling is occurring. Then from the labeling, there is the first reaction, that is the primary reaction, that is for of reaction of P, which is happening fast. The side reaction of O is happening slowly. Sorry, but we can see that the another side reaction of product A is also happening fast. So do we need this kind of reaction where the main application is happening fast and the one of the side reactions is also happening fast? I think so, no, because there will be electrons generated at two points, that is for the P reaction as well as the A reaction, and then it will be very difficult to know the reaction is being the electron is being generated from which reaction. This will again lead to false results. Okay, in the terms of B, same thing, just the reaction number is changed. So the O reaction is faster and the A reaction is slower. So again, that will again also lead to interference, which will lead to wrong readings being generated. In case of third reaction, it is even worse because here we are not getting even the primary reaction which we want to be faster. It will be slow. So all the readings which we will get will be completely wrong because we will get the readings from the byproduct rather than from the main analyte. And coming to the last option, here the primary reaction is happening fast and the other two reactions are happening slowly. The side reaction are happening slowly. So whatever electrons we get will be from the primary reaction. So that is the correct answer, which is option D. I hope I'm clear with my uh, explanation. In case it's not clear, you can always put your doubts in the comment section, or you can ask in the next lecture as well. Okay, so question 5. This is directly from the lectures. So, which in dash gene level is in with uncomplicated malaria, progress to cerebral malaria is significantly higher than in individuals with uncomplicated malaria. So the answer is PFHRR. So coming to the sixth question. So again, we have this reaction which is given in the lecture. So here we see that in this reaction, first EDC and carboxylic acid react with each other, and then they form some unstable compound, which then again reacts with NHS, and then they form a stable compound that is used for functionalization. So what is the unstable compound called? So that is it active O acyluria, active P acyluria, active N acyluria, or all of the above? So the answer is A, activo acyluria. So these things you need to remember them. Remember these reactions which are given in the coursework. There is, or else you may know them otherwise, but for this there is no trick actually to remember. So the catalyst or reaction product, if these kind of for these kind of questions, you need to actually look through the lecture slides. These are very simple questions, but these also test whether you are actually looking at the lecture slides or not. So this shows that it is important that you actually look at the lecture slides. So this is the answer. So coming to the next question. So Additional use of chemicals, enzymes, and electrode can cause unwanted site reactions that can substantially dash the signal levels and or dash the background levels, resulting into low signal to background ratio. So, we have already discussed about the additional use of chemicals and enzymes to that cause the site reactions. So if there are too many, if we use too many additional enzymes, the site reactions will increase. So that will actually lower the main signal level that we actually want to measure, and that will again add a lot of background signals to this to what we are actually looking for, and that will again elevate the amount of background signal. So the answer here is C. It will lower the signal levels of what we want to see, but it will lead to increase in the background level. So coming to the next question, Dash converts biochemical events into measurable signals, amplifier, op-amp, rectifier, transducer. So this is a very simple question. So basically, what does an amplifier do? Amplifier basically amplifies the signal. So it doesn't convert the signal; it just amplifies it. Whatever signal you give it, it will amplify and give it to you. Same with op-amp, that is operational amplifier. It will again take whatever you give and it will just amplify and give it to you. Rectifier is a electrical component that rectifies. So basically, whenever you have a AC signal, it has a positive peak, a positive zone, and negative zone. So, but DC is always either only positive or only negative. It doesn't have a variation in its profile. So here, rectifier actually converts the AC signal into DC signal. So that is what the purpose of rectifier is. And coming to transducer, transducer basically is a any um, device that converts signal from one form to another. So basically, what we are doing is it is converting biological elements into a major into measuring signal. So you can see, you can just find that the answer is transducer. So here it is. So basically, we have a bio component that is attached to a microtransducer. In a typical biosensor, we have a bio component that is attached to the microtransducer. Then to it, the analytes actually go and attach to the biotransducer bio component, and then there is the biochemical reactions occurring, the biochemical events that happen, and then there is the conversion of that event, that signal. Basically, through electron release, there will be electron release, and that will be actually converted into signal. So that is how the biosensing works, and the device that is responsible for conversion of biochemical events into the measurable signal is called as the transducer. So coming to the next question, no female commercial home blood glucose sensor works on which principle? Again, we have discussed this in practice assignment 0. So the answer is electrochemical sensor. So coming to the last question, that this is the question 10. Identify the scheme for this redox cycling reaction. So basically, this comes from the week 2 content. So, but I guess till this lecture is released, the week 2 content has also been released. So yeah, so from this we can see that it is a EC reaction. Yeah, so it is a CC reaction. So basically, EC or EN or EB reaction basically involve a transfer of electrons. So in this reaction, there is no transfer of electrons happening. So there is no electrochemical component in this reaction. From this, again, there in this, what is happening is the product is being converted at the active site. So from this, from the product, there are two chemical reactions being triggered. So basically, the initial product O1 is converted into R1, and again with the same reaction, P is converted into Q. From that, there is one more reaction occurring wherein R is being converted into O, and Q is being converted into P. So there are two chemical reactions occurring here, and there is no transfer of electron. So this is a CC type of redox reaction. So I hope I am clear with all these questions, and you are happy with what is being given. Um, in case of doubts, please write in the comment section. So if you also have any questions, write in the comment section, and we'll just wait for the so the questions as well. So, in case anyone has any questions, anyone has any questions, please write those questions in the comment section. In the actual session, obviously, we will actually talk amongst the participants and we'll discuss their questions. But since it's a recording session, we couldn't actually get you all those questions here. I deeply apologize for this. Um, so in case you have any questions, please feel free to put this in the comment section of this video, or you can ask all your questions in the next session as well. I would like to thank you all for listening to this video, and I would like to end this video with this. Thank you very much. Thank you, and I would like to see you next week. Thank you.